Great, welcome back to our first lesson in our last unit. So our last unit is on stoichiometry, or quantitative relationships and chemical changes. We are going to be looking at stoichiometry, but before that, our first lesson is going to be on net ionic equations. But before we kind of get through that, there are just a few little definitions we're going to get going through, just kind of clarify and just kind of get everything, all the terms out of the way first. So first of all, what is stoichiometry? So stoichiometry is just a method for predicting or analyzing quantities of reactants and products involved in a chemical reaction. So basically it's just a way for us to figure out if we have X amount of reactants, we can figure out how much of our product is going to be produced, or if we have X amount of our product being produced, how much reactants do we need or how much do we have. It's just a way of predicting and analyzing stuff. So just some of the words that we've been looking at. So we've seen this word show up before, qualitative. So qualitative is always like what. So we've got qualitative analysis of solutions in our last unit. So identification of chemicals involved. Now we're moving away from the qualitative and into the quantitative. And quantitative is how much of something. Now the experimental techniques that we use for quantitative analysis can be listed here. Our main ones are these right here. So our titration and filtration. Gas collection takes some very specialized equipment, and crystallization takes a lot of know-how as well. But either way, so you can use any of these types of analysis to get quantitative relationship because you're collecting or analyzing stuff. So when we look at crystallization, that's where we evaporate the solvent from the solution, leaving a solid whose mass can then be measured. So from that mass, that is how much of something, we can use it for calculations. Filtration, same thing. We form a product with low solubility, which we call a precipitate. It's formed in a reaction, and then we separate it by filtering it. And then, of course, the mass can then be measured. Same thing, we have a mass, we can figure out the quantity. Gas collection, that's if we, not accidentally, but if we form, if we have a reaction where gas is formed or used. So a gas formed as a product in a reaction is collected, and its volume, temperature, and pressure can be measured to determine the amount using the ideal gas law, of course. And then, of course, finally, titration. A titration, that's our entire last chapter, so chapter 8. And this is just a titrant in a burette. So these words will make a little more sense when we get into, what's a burette and what's a titrant. Anyway, we add a solution with a known concentration into a measured volume of sample to determine its concentration. So what we have right here is crystallization and filtration deals with mass. So our molar mass equation is going to use. Our gas collection revolves around our ideal gas law, and our titration revolves around our concentrations. So basically, we're going to be using stuff from Unit 1, Unit 2, and Unit 3 in this unit. And how we analyze stuff, we can either use graphs or calculations. And we are going to focus on our calculations. Now, when we are doing chemical reactions, there's a few things that do not or are not explained inside of a chemical reaction. And one of those is the conditions under which reactions take place. So we don't know if they're supposed to be at 500 degrees Celsius, 0 degrees Celsius. So what we're going to do, we're going to assume SATP conditions unless otherwise stated. So that just means room temperature and pressure at 25 degrees Celsius and 100 kPa. Now reaction also, just how it's written out, it doesn't tell us how long or the process, what's happening of the reaction. So it doesn't, from a chemical reaction, it doesn't say, let's sit for 5 hours. We just have reactants, products, and that's it. And also the measurable quantities of the reactants, only the type of and number of atoms. So that's also when we looked at general reactions, we never had the masses starting off or anything like that. So that's where just chemical reactions don't explain that, but of course we will get more information from questions as we read it. Now there's also a few assumptions that we're going to put inside of equations as well, or reactions. And that is, one of them is all reactions are going to be spontaneous, meaning that if we have reactants reacting, they are going to react to produce products. That's it. We're not going to learn anything about, this reaction won't occur. We're always going to have our reactions occurring. Now another thing, all reactions are fast. Now there is no indication on the rate of a reaction, but we are going to assume that they're fast. We just say, put our reactants together, boom, we get our products. We know that's not always the case, but that's what we're going to assume. Now, another thing we need to assume is reactions are going to be quantitative, meaning that they go to 100% completion. So that is that all of our reactants react to produce our products. Now, we are going to learn later that that's not always the case, but for now, that is an assumption that we're going to make. And of course, the last assumption we're going to make is reactions are stoichiometric, and that is they react in their simple whole number ratios, or they react per their balanced chemical equation. Now, this is an assumption, but from a lot of chemical analysis, we know that this actually happens, especially the way we have our chemical equations written out. Now, like I said, today we're going to focus on our net ionic equations. Now, this already showed up a little bit in last unit, but it was only for acid and base neutralization reactions, so we're going to extend this concept of net ionic equations into all different types of reactions, so single replacement, double replacement, combustion, every type of reaction we can assume. So, as we kind of learned before, in a net ionic equation, what it is a chemical reaction whose equation includes only the entities that react and omit stuff that does not change. And the things that do not change we call spectator ions, and they are present but they do not take part in a chemical reaction. So the rules are going to be very similar to what we've done with our acid-base reactions. First, we're going to write a complete balanced chemical equation, and of course assign states of matter. And the reason we need to do that because we're going to dissociate all highly soluble ionic compounds, ionize all strong acids to show the complete ionic equation. Now, this is where you have to remember, molecular compounds don't ionize, so they stay the same. Weak acids, their major entities is not the hydrogen ion, they stay together as well, so weak acids do not change their formula, and low solubility ionic compounds remain intact. It means we do not ionize or dissociate them. And of course, we cancel identical entities that appear on both the reactant and the product side. So basically, we cancel out things that do not change. So we're going to look at our first example. Or it says here, note when eliminating canceling spectator ions, they must be identical in every single way. So same charge, same coefficient, same everything. So our first example, we have student A mixed solutions of lead 2 nitrate and sodium iodide and observed the formation of a bright yellow precipitate. Another student recorded the same observations, but they used lead 2 nitrate, but they mixed magnesium iodide instead. So we have a change in reagents from sodium iodide to magnesium iodide, but we still have this bright yellow precipitate being formed. So what we're going to do right now is look at the net ionic equations to see if these reactions are any different. So first for student A. So student A mixed a solution, so we know a solution is already aqueous, right? So that means we have PbI2AQ plus our sodium iodide. Same thing is that it already says it's a solution, so we don't need to check our solubility charts. We can just go write AQ. So by looking at, we have an ionic compound and ionic compound. This is a double replacement reaction where the sodium and lead are going to change places. Now, please remember that when you're doing writing out your products, redo the drop and swap method. So that means lead 2 pairing up with iodine, we have Pb2 plus, and iodine is 1 minus. So when we do the drop and swap, the 2 is going to drop, swap in front of iodine, the 1 goes in front of lead. So our new formula is PbI2. Now I don't know its state of matter, so I'm going to keep it blank. And then our next one is going to be, lead 2 nitrate. I don't know why I had lead 2 iodide here. Sorry, so just go back and change that. Lead 2 nitrate, PbNO3, 2. Sorry, and this is aqueous. So that's our lead 2 nitrate. So if you're wondering what I was writing down there, yeah, I just see my error. So this is our first one. Now our next one, sodium and nitrate are going to pair up. So same thing. Check your periodic table. Sodium is just Na plus 1. Nitrate is NO3 minus 1. So this just turns into NaNO3. And we don't know the state of matter, so I'm going to keep it blank. Now we can balance and then kind of write out our ionic equation if we want, or figure out states of matter, but let's balance anyway. So we need 2 nitrates and 2 sodiums, and that's how we balance that one. All right, so now we have 2 iodines, 2 iodines, 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates. Now as for the solubility chart. So sorry, I should have had that fired up already. So solubility chart looks something like this. So we need to check our two new compounds. So we have lead iodide and sodium nitrate. So we'll do sodium nitrate first because our nitrate anions right here. Most things are soluble. We have a quick scan at the exceptions. We don't see sodium down here. So we know sodium nitrate is very soluble, so that means AQ. So we can go back and write AQ. Now for our lead 2 iodide, we see iodine right here. Most things are soluble, luckily, but we see lead 2 plus slightly soluble, so that stays as a solid. Excellent. Now, for our ionic equations, as it said on the previous page, we dissociate all soluble ionic compounds, ionize all strong acids, everything else, it stays the same. So that means anything that has AQ, we ionize. So that means our lead 2 nitrate, we ionize into the lead 2 plus, so we basically just apply an ionization equation, plus we get 2 nitrates, our sodium iodide, we also dissociate, keeping the coefficients as well, right? Because we have 2 sodium and 2 iodines, so 2 sodiums and 2 iodines. Finally, our lead iodide, this one stayed as a solid, so we keep PbI2 as a solid, and then this one's aqueous. So we dissociate that as well. Now, this does look a little bit messy, but now we are going to go through the process of canceling out entities that did not change. So by a change, like if we look at the lead example, we see lead 2 plus forming lead 2 iodide. So this is an ion forming a solid. So that is a change. When we look at our nitrate example, we got 2 NO3 minus aqueous, 2 NO3 minus aqueous. The nitrate ion did not change. So we're going to cancel that out and move it down here into our spectator ion. Now also we'll notice the sodium 2 Na plus aqueous, 2 Na plus aqueous. Sodium also did not change, so that is also a spectator ion. And the iodine changed. So our net ionic equation, we have our lead 2 plus ion reacting with 2 iodine ions producing lead 2 iodide solid. So these are the only ions that actually reacted to produce a solid, whereas the sodium and the nitrate did nothing. So next one, so student B, we are going to do the exact same thing and see if these are different reactions or not. And the only difference is that a student had lead 2 nitrate mixed with magnesium iodide instead. Right, so our balanced chemical reaction, we have lead 2 nitrate plus magnesium iodide. There's a double replacement reaction. Magnesium then pairs with nitrate. Now remember, magnesium is 2 plus, nitrate is NO3 1 minus, so we do our drop and swap, we should get this. I don't know the state of matter. And finally, we get our lead 2 iodide. Now, because we already did this one up here, we know lead 2 iodide is going to be a solid. The only thing is the magnesium nitrate we don't know about. So just a quick little check to see if it is going to be aqueous. Our nitrate's right here. We look down here. Magnesium does not show in these exceptions. So Mg2 plus is here, meaning that it is very soluble. So that means AQ. And then of course when we do our ionic and our net ion and our spectator ions, but no surprise, please write in the ionic if you want to, but I'm just going to jump to the main point right here, is that this should be your net ionic and now your spectator ions should look like this. All right. Now I know I kind of left off the ionic equation, but it is going to look something like. So it will look something like that, and you will notice as well the only things that does not change: magnesium and the nitrates. So that is net ionic equations. Now I'm going to go over example the second example, example 2 with you guys, and then I'm just going to ask you to try the other ones on your own. And I'm just going to put up the answers, and then of course, when you go through your notebooks, has a lot of these here as well that you should definitely try. But what we have here, next one, write out the net ionic equation for the reaction of zinc metal with aqueous copper 2 sulfate. So this right here, we start off with zinc metal is a solid plus aqueous copper 2 sulfate. So it's telling us it's already aqueous. So you can tell this is a single replacement reaction where copper and zinc are going to change. So copper is our new element, and our formula for zinc 2 sulfate, zinc is 2 plus, sulfate is SO4 2 minus. So when we do our drop and swap, it's that. Now I don't know what zinc 2 sulfate will look like, if it's aqueous or solid, so I go back to my data booklet. In this case right here, I find my sulfate right here. Most things are soluble, which is good. The only exceptions, calcium, strontium, barium, silver, mercury, lead, and radium. So obviously, zinc 2 plus is in the most very soluble. So we write AQ. Now, our ionic equations. Everything that have aqueous, we break apart. If it's not aqueous, it stays the same, meaning that zinc solid, elemental zinc, stays as zinc solid. Our copper 2 sulfate, because it's aqueous, that means we separate it. So you get Cu2 plus, aqueous, plus SO4 2 minus, aqueous, producing elemental copper. Will not dissociate, it stays as copper. And because we have zinc 2 sulfate listed as aqueous, it dissociates into that. Now a quick scan, we will see zinc going from zinc solid to zinc 2 plus. That is a change. We're starting with a solid element turning into an aqueous ion. So that's a change. We see copper 2 plus, so an aqueous ion turning into copper solid. That is a change. Sulfate, SO4 2 minus aqueous. On the other side, SO4 2 minus aqueous. Sulfate did nothing. So sulfate is our spectator ion, or in this case, our reaction is zinc plus copper 2 plus is producing copper solid plus zinc 2 plus. That is our net ionic reaction. So definitely pause the video here now and try the other ones, but I'm just going to put in the net ionic equations for example 3 and 4. So example 3, we have hydrochloric acid and barium hydroxide, and example 4 is net ionic equation between elemental magnesium and hydroiodic acid. So see if you can get these on your own, and the answer is going to go up in 3 seconds. And the net ionic equations should look something like this. So for the acid-base neutralization, it depends on if you use Arrhenius or the modified Arrhenius theory to get the ionization for the acid. If you just use H+, that's fine. You get H++ OH produces water. And then of course, or H3O plus and OH minus produces 2 water. You get the exact same thing. And then of course, for the other one, the elemental magnesium and hydroiodic acid will look something like that. So that's it for spectator ions. The thing is though, with these here, you need to have lots of practice with them. So inside of your CYU book or your workbook, there are plenty there, so please try those, and definitely try to get through all these before you start with the gravimetric stoichiometry, which is going to be our next lesson, because you need to have as much practice as possible writing out these equations, whether it's just step 1, the balanced chemical equation, or the net ionic equation. So that's it for this lesson, so I'll see you guys for the next one, which is going to be looking at our first set of stoichiometry.